Hello, everyone. Welcome to today's webinar, where we'll be discussing how to link hydrogeologic and geomechanical models for mining using two of ITASCA softwares, MINEDW and iMat. During this webinar, we will demonstrate the key features of MINEDW, including the seamless implementation of geology and the simulation of open pits, dewatering, and depressurization. The webinar will also demonstrate how to export MINEDW-calculated pore pressures for different stages of excavation into an iMat readable format. We will then import this data and build a geomechanical model which can be used to estimate displacements and factor of safety. Whether you're joining us from an academic or consulting background, our goal is to show you the ease and benefits of combining these applications so that you can apply them to your own projects. As mentioned previously, we'll be integrating two of our softwares, MINEDW and iMat. MINEDW is a three-dimensional, finite element groundwater flow program that has been developed specifically for mining applications, whereas iMat is a geomechanical toolbox intended to make model construction and mining analysis easier and more efficient. During this webinar, we'll examine a case study of an African mine to demonstrate the ability of ITASCA codes at simulating groundwater conditions and slope stability by combining the results of a groundwater flow model in MINEDW with pore pressure analysis in iMat. To begin, my name is Christian Ramelis. I joined ITASCA Denver at the beginning of 2024 as a staff hydrogeologist. During this time, I've had the opportunity to work on several open pit mines where I've used MINEDW for hydrogeologic analysis and predictive simulation. Before joining ITASCA, I completed my MS at Ohio State University and my BS at the University of Texas at Austin. Co-presenting with me today is one of our iMat experts, Jim Hazard. Jim has been with ITASCA for 15 years and is currently one of our principal engineers in addition to software manager. Jim received his PhD in numerical modeling of acoustic emissions and dynamic rock from Keele University in the United Kingdom. He also received his BSc in geological engineering and geophysics from Queen's University in Canada. In addition to all the work Jim does here at ITASCA, he is also a dedicated member to several professional organizations. The project we'll be discussing today involves an open pit mine located in Africa. This mine requires extensive depressurization of low permeability units and dewatering operations of high permeability units to ensure dry working conditions. Pumping rates at the site can exceed over 1,000 cubic meters an hour, with inflow coming from groundwater storage, precipitation-induced seepage, direct precipitation, and surface water runoff. To mitigate this excess water, the mine has installed sub-horizontal drain holes and dewatering wells to control groundwater inflow, intercept groundwater flow behind the pit, and depressurize the open pit wall. Additionally, the sites use drain holes and low permeability units to reduce water levels to meet geotechnical targets. ITASCA's role in this project was to use the provided groundwater level, dewatering rates, and geologic mine plan data to update and calibrate a groundwater flow model. Once model calibration was complete, we used the model to predict groundwater inflow into the open pit and determine pumping rate requirements under various optimization cases. Data from the initial model runs were used by geotechnical engineers to assess slope stability. After the initial slope stability assessment, ITASCA updated the future predictions to include sub-horizontal drain holes to reduce water levels in low permeability units. With the completed calibration and predictive simulation, we provided an assessment of overall groundwater flow, model uncertainty, and recommendations for future dewatering and monitoring at the mine site. Our goal with this groundwater flow model were to use the results to predict future dewatering requirements to maintain dry working conditions and predict depressurization of the open pit high wall by adding horizontal drain holes. The modeling project consisted of three main objectives. The first objective was to compare groundwater flow simulation results with recently collected groundwater level data within the open pit to determine if our model was properly calibrated to ongoing dewatering and depressurization. Once the model was calibrated, we could use the model to simulate future mining. Iterative predictive results were then used to determine where we could put drain holes to ensure proper depressurization of the geologic units to meet the geotechnical requirements. Finally, we provided guidance on the horizontal and vertical spacing, length, and total quantity of the drain holes to meet depressurization requirements simulated in the model. Here, we have a picture of our open pit modeled in MINEDW with cross-sections shown at different time steps throughout the mine plan. Cross-sections are helpful because they can allow you to visualize the water table and pore pressures at different time steps within your model. In the middle, you have a cross-section where you can see much heavier lines around the open pit, which is the more refined vertical discretization, which consists of smaller elements that require more computing power, but ensure more accurate modeling. Increasing the discretization is important around these areas to ensure the most accurate model, but doing this across the entire model would take too much computing power and will slow down your work. Below that cross-section, we are zoomed into the pit where we can see the water table and the drain nodes that were placed. Drain nodes are placed in areas where the pore pressure is high to ensure proper depressurization and prevent pit wall destabilization. MINEDW can be used to simulate various drain hole designs across open pits to meet these geotechnical requirements and target levels behind the pit slopes. As with any model, challenges arise surrounding the amount of data that is available and provided. In this particular project, groundwater data was limited around the pit and in the low conductivity units where high pore pressures may be a concern. Limited groundwater level data makes calibration more difficult and can affect the accuracy of the model. Highly permeable features also provide challenges as they are conduits of high hydraulic conductivity and groundwater flow into the open pit. As a part of the analysis, ITASCA provided an assessment of the model uncertainty and potential range of dewatering requirements and depressurization for future mining. An overview of the model setup. So during this webinar, we will go over how to create a mine plan and set up an open pit, as well as import dewatering boreholes and their dewatering rates. We will then import the geology to allow us to create cross sections to visualize pore pressure, and then we'll export these pore pressures for analysis in iMat. Here we have a video that shows an open pit excavation in MINEDW from the mine plan. This pit is imported as a DXF provided by the client, and then mine schedule will be created to show the real-world excavation of the pit according to current and future mining. When creating a mine plan, there are two options for interpolation, including depth and volume. When choosing depth interpolation, the excavation will occur downward and outward simultaneously, whereas the volume interpolation will only move downwards instead of outwards, with the rates defining the amount of volume excavated. To create an open pit in MINEDW, you'll need the DXFs of the individual mine phases provided by the client. In order to make a mine schedule, these must be converted to a .dat or .text file, which can be done in MINEDW. You'll go to the attributes table and then click the button at the bottom that says to data file. Do this for all DXFs, and then you can import them into the mine schedule here. You'll then want to make sure to choose the correct start and end date for each individual mine phase, and then choose how you want to interpolate it, whether that be depth or volume. You'll also want to make sure to import an ultimate BLN file, which is a file that contains the boundary of the pit that will be excavated. At this point, I typically like to save my mine schedule. That way I don't have to go in and re-import all this individually again, and I can just import it all as one. Once you have that saved, you can go to create a mine plan, and then you can choose the directory where you'll want to save it and name it. Now that the mine plan is created, you'll want to go to mining, open pit, and then here you can add your new mine plan that you just created. You'll want to check the start date and the pit bottom elevation, make sure those are correct, and then add in the evaporation if you know it for your site. Once that is all entered, you can click OK. Now I want to show you how to import in the dewatering wells and their dewatering rates into MINEDW. To create dewatering wells, you'll want to go to create, and then you'll need to import a DAT file, which will contain the number of boreholes at the top, followed by the name in parentheses, and then their X, Y, and Z data. Once you add in all your individual boreholes, you can then import a time series of all the dewatering rates for each borehole. This is an example of how that file will look with the name, the node, and then their 0, which correlates to the pumping rate, pumping type. You'll either want to choose pumping rate for current pumping rates, and then if you're doing predictive simulations, you'll typically choose LPE. You'll then follow this with your screen top and screen bottom, which you'll also import here. Once you have your dewatering boreholes and their rates into the model, you can move on. To import the geology, you will once again need DXS provided by the client. You'll want to go to DXF by going to List, File Data, and then DXF, and then you'll be prompted with this box right here. You'll want to choose to zone the rock that you just imported, and then you'll typically want to select volume or center before clicking OK. It might take a minute to load, but once it does, your geology will populate, and in our example, our geology is visualized right here in the blue. Now that the geology is in the mine schedule is defined, you can visualize the cross-section or the pore pressures in a cross-section. Here you can see the pore pressures at different depths throughout the pit, and then these pore pressures can be exported under results where they can be analyzed in MINEDW. There are three options to export pore pressures. When you go to the results page and you scroll down, you'll see three export options, including export pore pressures, export cross-section pore pressures, and export pore pressures to FLAC3D. When you click export pore pressures, you get a box that shows up that will allow you to choose the units, whether you want to do meters of water or kPa. You'll also get an interpolation method, which you can choose here. With the export pore pressures, you get to export them in 3D, so you can choose your domain of X, Y, and Z, and you can also edit the number of lines so you get the correct spacing that you like. When you export cross-section pore pressures, that will be in 2D. Once again, you'll be prompted to import the unit you need and the interpolation method, and then you can also modify the X and Y domain. For what we're doing today, we're going to want to export our pore pressures to FLAC3D, which will also export them in a 3D format across our entire domain. Once we do that, we can now hand this over to Jim, who will show you how to analyze the pore pressures in iMat.
This is Jim Hazard. I will now talk about iMat. iMat stands for ITASCA Mining Analysis Toolbox. This is a relatively new piece of software being developed by ITASCA, and its purpose is to help you with geomechanical analysis specifically for mining applications. So right now this is being used for underground mining applications and also surface or open pit mining. The original plan for iMat was to provide a wrapper around FLAC3D to make it easy to solve these geomechanical models specifically for mining applications. We've done that, but in addition to this capability, there are other capabilities to help you with your mining analysis that I'll talk about a little bit in a minute. Specifically for this webinar, the important part is that iMat also allows you to import pore pressures that come from MINEDW and use this in the geomechanical analysis when you're looking at stability and displacements and so on. Okay, so if I drop out of PowerPoint here and we go to have a look at iMat. So this is what it looks like. You can see that this is more of a GUI-driven application than our traditional FLAC3D application. And what you'll see here on the left-hand side is a series of components, or we like to call them modules, that you can use when you're doing these geomechanical analyses. So, for example, we've got geometries, which I'll talk about in a minute, spatials, block models, so you can import and visualize block models and use them with your modeling, the FLAC3D components, charts, information related to seismic, microseismic, importing, visualizing, interpreting, boreholes, movie makers, and so on. I don't have time, of course, to go through all of these things, but you can see how this is more than just FLAC3D. There are other components here. So what I've done is already set up a blank iMat project here. You can see here the project settings. There's a name for the mine, time zone, reference system, unit system, and so on. So right now, this is just an empty project with nothing in it. We can start by importing geometries. So if I go here to the geometries module and I expand this, you can see I've got caves, development, geology, pit shells, and so on, right? So let's start with the pit shells. I can right click on here and just say import a geometry. This is the DXF that was provided by the mine. I just say okay here. I don't need to convert it from anything to anything else. It imports the open pit. I can zoom in on the extents here by clicking this little magnifying glass. So here's the open pit that I just imported. Note that this is the final state. We could, in theory, create a model where we do this in a staged excavation, bit by bit and getting deeper and deeper. In the interest of time, I will just start with the final state here. You will also notice that this geometry is just a set of contour lines. It's not actually a meshed surface. And iMat has the ability to deal with this, which is actually pretty cool. Okay, so we have an open pit. We also have with this mine a geological surface that defines a geological unit. So I can right-click on geology and import a geometry for that. And again, here's the geology that was provided by the mine. Say, okay, I need to visualize this, so I can click the little light bulb next to the geology here. And there it is. And in this case, it is a meshed surface, and it's a closed volume that defines some geological unit. I think it was a breccia in this case. And so we'll use that in the FLAC3D model in a minute. So we've imported our geometries, and the next thing to do is create the FLAC3D model itself. So obviously we're doing the open pit version here. I can go to the FLAC3D open pit module, right click and say new FLAC3D project. Call it whatever I want, MINEDW project. Now here's the important part. We need to tell it how we are receiving the pore pressures, either, for example, a fixed elevation or some depth below the surface. More common, you may import a geometry, which might be a DXF that defines the water table. In this case, we're actually importing the data from MINEDW. Okay, so it's created the FLAC3D project. If I expand this, you can see a series of subheadings. And the whole goal with iMat here is to try to make it easy to build these models and do the interpretation. And what you want to do is work from the top to the bottom, filling in things as you go. It sort of gives you direction about how to do these things and tries to make it as easy as possible. So if we just start from the top and go down, the first thing we have is in situ stress. By default, it assumes lithostatic stress, meaning that it will calculate the vertical stress in the model based on the depth below the surface and the density of the material. It does that for you. The only thing you necessarily need to specify here is the ratio of horizontal stress to vertical stress. In this case, we'll just leave it as 1. So going down the list here, the next thing is the mining sequence. So what we need to do is add a mining sequence. So I say new, and a series of mining steps. Again, you could, in theory, have multiple steps here where I excavate the pit piece by piece. So I could choose a number of steps here greater than 1. In this case, we'll just go straight to the final pit. We'll just do it in 1 step. And in this case, the dates and the durations don't really matter. So I just say, okay, I've got 1 mining step here. For this particular mining step, there needs to be a pit shell, which of course defines what it is that we're mining. So what I can do here is I can just go up to the pit shell that I imported under the geometries, grab it, and drag it down here to the pit shells that it's going to use for the model. Okay, so I'm done. So I've only got 1 pit shell here. When it actually creates the model, it will sort of regenerate that pit shell to close in some of these holes and things like that. It does that for you automatically. You don't need to worry about it. That's just what this next component here is. The next thing we need to do is import the pore pressure. So this is the important part here if we're worried about, the results from MINEDW. So pore pressure grid, I've already told it that I'm expecting to import some sort of grid of pore pressures. So all I need to do here is right click on it and say import. I can choose a CSV file or a MINEDW file. So the MINEDW grid. So in the first half of the webinar, Christian exported a MINEDW grid in FLAC3D format, and that's what these MDP files are. We'll choose the first one. This is end of mine pore pressure.mdp. So I open that. Takes a couple seconds to import it. Okay. Now I want to look at it. So let's first just hide this big geology here by clicking on the light bulb. And then I want to visualize the pore pressure here. So you can look at just the grid, which will just be a bunch of dots, or you actually want to see the pore pressures. So this is what I actually want. So I'm going to click the light bulb to see the pore pressures. It just shows me a blue line here. What's happening here is that the MINEDW model is way bigger than what the geomechanical model will be. It was more of a regional type of groundwater analysis. So we have a very large grid of pore pressures here. I can zoom to the extent of that, right? And so you can see my little tiny pit here with this very large grid of pore pressures. So if I want to, I can zoom in on this thing here. What I want to see, of course, is the pore pressures close to the pit. This is just a cross section, right? It's a whole 3D grid of pore pressures. So I could sort of try and translate the cut plane. It's easier just to pick a point here. The point, there we go. Okay. Okay, so now I can see the pore pressures around the pit. Let's zoom in a little bit more. Right, I can actually smooth out these contours a little bit here. So you can see, as you would expect, a sort of depletion of the pore pressures under the pit. This is what we expect. Okay, so we've got our pit, we've got our pore pressures. The next thing going down the list here is to define a pit region. Because again, the geomechanical model will be smaller than the pore pressure model from MINEDW. So what we want to do is define some sort of region over which we're going to do a detailed analysis of this thing. In this case, it's pretty obvious because we have a relatively well-defined pit. And sometimes in models, you might have a very large topography or something like that, and you would need to tell it where the area of interest is. In this case, it's relatively easy. So I'm just going to hide these pore pressures for now, and I need to define this pit region. And so I can sort of automatically do that just by clicking on this little box here over to the right. So it automatically defines a pit region. Oh, and I want to visualize it by clicking on this little light bulb again. So you can see, let's turn off the pore pressure grid, sorry. So what you can see here is that it automatically drew a box around the pit, and I can do a top-down view. Right, so it drew a box around the pit, and then if I look at the 3D view, you can see that it's deep enough to include the whole pit, and so I don't need to do anything else here. It's possible that I could move these points or add points to get a better representation of the pit region. In this case, I'll just use the default that it came up with. So this is essentially defining my area of interest. This is where I'm going to have a more detailed model. And it's also the region where it will weaken the material when doing a factor of safety calculation. So this is just the area of interest, but of course we want the boundary of the model to be further out than this region here. So the next part going down the list is the model domain. And so again, I can just automatically calculate that by clicking the little box here. It says done, and then I can visualize it by clicking on the light bulb. And let's just hide the pit region. So now I've got a model domain that is bigger than the pit region, right? Because I want my model boundaries to be further away. And you can see that it intelligently figured out where the boundaries of the model should be. And again, I can adjust this, but in this case, I don't need to. Okay, we're almost done here with the model building. The next step is the materials. So I look at the materials. By default, you're given a host rock material, right? You can assume that everything is just the same material. And all we really need to do here is assign properties to it. So for constitutive model, you don't want to do elastic because that's not very interesting. Often in these open pit type models, we would choose a hook brown type of material. So I tell it to be a hook brown material. For this particular mine, the host material is mostly limestone. I'm going to assume that it's a relatively weak limestone. I can just put in some properties here. So 10 gigapascal Young's modulus, let's say 2,600 kilograms meter per cube density. Again, let's assume that it's, it's limestone. It's got a fair amount of fracturing or jointing in it. So let's say GSI 50. Let's say sigma CI would be something like 20. And then everything else we can just leave as default. And great, happy with that. Now, remember we imported that geology surface. So we can also specify a different material type for that breccia. So what we can do here under materials is right click and say make a new material domain from a geometry. And I can say use this geology that I imported to define that region. Say OK. And you can choose a distance from geometry. So imagine you were importing like a fault zone. You could say, find everything within 100 meters of that geometry and give that some different set of properties. In this case, we want everything inside of the geometry. So I choose this one here, polyhedron geometry. Say OK. All right, so I've got this host rock and I've also got geology. That's not a very descriptive name. I can just rename that. Let's call it breccia. And then again, I just need to set the properties for that. We'll also make that hook brown. And let's assume it's maybe even a little bit weaker than the limestone. So let's say Young's modulus 5, density 2500, GSI, let's make it 30. MI, let's make that 8. Sigma CI, let's make that, I don't know, 10. 10 is fine. Okay, so I've got my host rock and I've got my breccia. The last thing we need to do here is actually build the model. So we don't really need to do anything here. Well, let's just have a quick look at what it's going to do. So if I go back to model domain, oh, I did skip over a couple things here. So after I created the model domain, what I should do is look at the boundary conditions. I actually don't need to do anything because the default is fine, right? You've got roller boundaries on the sides, free on the top, and fixed on the bottom. This is fine. But the other thing I can do here is look at the refinements. So what this is it's creating, it will create FLAC 3D zones. And it will be, the zones will be smaller close to the pit, and it will be larger further away from the pit, right? So similar to what was discussed in the first half of the webinar for MINEDW, iMat will do exactly the same thing, which give you smaller zones close to the pit and larger zones far away. And you can see what these refinements look like here. Okay, so if we're happy with that, all we have to do here is go and create the grid, right? So I just right click on it and say build grid. Reconstruct pit shells and water tables. So as I said, it will take this geometry that we imported and it will sort of fix it up a little bit for us and fill in the holes and things like that. So I want to do that. I want to create the grid, obviously. I want to apply the material domains, obviously. And I want to apply the mining sequence, obviously. So most of the time you would select all 4 of these things. And I hit OK. And this will take 2 to 3 minutes. So I'll just pause the recording and come back again in a second. Okay, we're done generating the grid. You can see it took 4 minutes and 49 seconds. I hit OK. You can see over here, it's telling me the grid has 1.7 million zones, which is fine. I can solve this kind of thing on my laptop. It's no big deal. So let's just quickly look at the refinements to make sure this worked. Let's hide the model domain. And you can see here under the grid, I could plot the grid points, which again is a bunch of points. It's not that helpful. But what I can do is look at the refinements. And so let's have a look at the 5 meter zones. So if I turn that on, by default, it plots them as points. And there you go. So see in yellow here, these are all the 5 meter zones. I could actually plot them as faces so that they look like zones rather than dots. Just takes a little bit of time to generate the plot. There you go. So this is kind of what the FLAC 3D model will look like. These are the smallest zones. And then, of course, the zones get bigger as you move out from the pit, right? So this is great. We're happy with this. Let's just hide that. And now we're basically done. All we have to do is solve it. And then we'll come back and do the post-processing. To solve it, you just go up here to model and hit this little play button. And it says, would you like to solve this project in FLAC 3D? So what that will do, you have a choice here. You can actually have it spawn FLAC 3D and put the data file in there and run it. You can run it in FLAC 3D yourself, or you can just say no. And it will actually, in the background, spawn a FLAC 3D with no interface. And it's just be producing the output here in the console. And so now it's going off and doing its calculation. For a model of this size, if you include the factor of safety calculation, it will probably take a couple hours maybe. So again, we'll stop the recording and come back in a minute. Okay, we're back. The calculation is finished. We're going to do a little bit of post-processing now. So here's the pit we were just looking at. The calculation is finished and the results exist, so I can now look at them. So the first thing, if I look under post-processing here, I choose the active mining step. In this case, there's only one, so it's easy. In other examples, they might have multiple steps that you might want to look at. I can go down the list here. I can look at a cut plane. So if I turn on this light bulb to create a cut plane, you can see by default, it's plotting displacement magnitude. I can choose this drop down different things, stresses and strains and so on. Displacement is not a bad thing to look at. So here's the cut plane. showing displacements through the pit here. Let's just hide that pit for now. Right, so we can see the maximum displacement here about a little bit, probably less than 6.8 centimeters. I could actually go here to these controls and move the cut plane along and sort of scroll through the pit and see how the displacements are changing. This is useful to get a better view of the displacements on the whole pit. Instead of plotting just a cut plane, I could actually plot the pit surface here. So if I just choose under post-processing pit shell, again, it's defaulting to displacement. So you can see here, let's just zoom out a little bit, the very high displacements right where you have this sort of bullnose structure here. Again, around about 6.8 centimeters as a maximum. If just quickly turn on the geology here, you can see that where we see this high displacements also corresponds to where we have some of this weak breccia material. So this totally makes sense. This model actually solved, it was 6.8 centimeters, but it's stable. What you generally want to do is calculate factor of safety. And the way that works is that it sort of weakens the material by different degrees and then sees if it's still stable. And by using the amount of weakness that you have done, you can figure out the factor of safety. So this calculation has already been done. I can go here, let's hide this displacement pit shell and show factor of safety. Already played around with the contour limits here a little bit to save time. But what you can see is maximum factor of safety 1.5. So everything that's blue is super safe. And then as you get towards more red colors, the factor of safety gets lower until you get to this, again, this bullnose region here where the factor of safety is probably around 1.1 based on the colors. So this is maybe where you want to be a little bit worried about your pit. If you want to get more exact values here, we can pick points on the pit surface here. So one of these tools, this one says get value at a point. So I can click on that and I can just pick here and see, okay, that's 1.1, 1.1. So it looks like our sort of worst factor of safety is about 1.1, which is still worrying, but at least it's stable right now. There are many other things you can look at here, but in the interest of time, I think I'll just wrap it up. And that will be the end of the webinar, and we're happy to answer any questions that you might have.